Hello, everyone. So today we're going to talk about the time series analysis. So before I start, I would give you the outline of the lecture. And we're going to cover the following points in today's lecture. So we're going to talk about the definition. We're going to talk about the different types of time series, or I should say we are actually going to be talking about two types. So we're going to be talking about a stationary time series and a non-stationary time series. Okay. And we will talk about one of the possible econometric problem, which we call spurious regression. Okay. We will also talk about how can I check which type of time series I have. So we have some tests that we can perform. So how to check the type of time series. We have multiple tests that we can perform. I'm going to focus on, actually, I'm just thinking, so maybe I'm going to give you two non-formal tests and one formal test. So we have three types. We have an autocorrelation test, the partial autocorrelation test. We have also the Pierce box test. And actually, I'm going to give you one more. Okay, so the Dickey-Fuller test. This is a very famous test, okay, DF test. Okay, so this is my plan for today, and I hope that I can cover all these points. So let's start. You already know that a time series is like, so what is a time series definition? So time series is like any variable, right, over time. So this is time, okay, and this is, let's say, GDP. Okay, so if I'm trying to graph GDPs from the 1990, 1995, 2000, 2005, let's say I have here, this is 2005, any day, any year. So if I'm trying to look at how the GDP is going over time, okay, and these are the different values of GDP. Let's say this is in dollars, in millions of dollars. Okay. And this is actually, this is a time series. So GDP here, we're seeing a variable that is analyzed or graphed over time. And this variable, or we can define it as any time series data are those related to a specific entity, right? So I have just one cross section, okay? So when I say a specific entity, you can think of this as one country, one student over time, right? Any cross section. One government, one region could be just like an average of a group of countries. So we consider it as one region, okay, and so on. And this is analyzed over time, okay? So I have the example is the GDP of USA over the period from 1990 all the way to 2005. So this is an example of a time series data set. Okay, of course I can have like GDP as a function of inflation. So if I have the variable GDP and now I have a different notation, which is T, I don't have I anymore in this topic, is equal to beta naught plus, I can think of what factors affect GDP. Let's think of it as in like inflation, again, over time T, plus beta 2, let's say unemployment T, plus UT. So this is a time series model in which I'm trying to estimate the factors affecting GDP over time. And this is related to just one entity, which is, for example, USA over a specific period of time, which is more than 1 year. It has to be more than 1 year and to be considered as a time series. And here in our example is from 1990 all the way to 2005. So there are different types of time series. So of time series data. So the different types of time series, I don't like the P. So types of time series data. So we have basically two types that we are going to talk about them in today's topic. So the first one is called the stationary process, okay? What is a stationary process? By definition, a stationary process is a process that has its mean, so the average of GDP, the variance of GDP, and the covariance, again, of GDP with itself, or we call it at various past values, or the past values in econometrics, we call it lags, okay? So it covariance with a variable and itself. It's a covariance of the variable and its previous lags. We call it, or previous points in times. So at previous lags, okay, remain the same, okay? So, and this is like regardless or no matter what time we measure it, okay? So you can think of it in statistics term, you can think of it as this variable has constant probability distribution. You think of it this way. The variable is like, looks like this. So if you think of this variable as GDP, and I'm not saying that GDP is always stationary, I'm just giving you an example. So if this is GDP, and again, this is time, okay? And if the variable looks like this, it moves up, down, probably a little bit up, down, and so on. Okay, or let me just give you, because we have different types of stationarity, so let me just make it kind of strong stationary, because we have strong stationary, we have weak stationary, and so on. So let me make it strong stationary. So it's kind of similar. And the mean, as you can see, is constant. I do have some points above, some points below, but on average, the GDP goes around a constant average, or constant. In time series we call it trend, okay? Or you can think of it constant mean, okay? So this type of time series is non-problematic, right? I see what's going on with the GDP over time, and this is, let's say, from the 1990, let's say this is any number, okay, 2014, I can see how the GDP is performing over time. And now suppose I want to predict what's going to happen in 2015. It's easy because looking at the past values or the past behavior of this variable, I can probably predict what's going to happen in the future. It doesn't seem that this variable moves randomly. It seems that this variable moves with a constant behavior, right? So I can predict the way this variable is going to behave in the future. So we can always think of stationary process as a non-problematic, right? Or problem-free. Let me write it as, I'm gonna write it as problem-free. It's kind of, so let's say it's a problem-free variable, okay? A non-problematic variable or problem-free variable because it's easy to predict. I can see what happened in the past. I can predict the future and so on. A non-stationary process is just the opposite, okay? So non-stationary process is, it's actually like the easiest way to define it is if the time series is not stationary in the sense just defined. So if you find the variable has its mean, its variance, and covariance does not remain constant, okay, over time. It keeps changing. It has this graphic, it could have like different graphical representations. It could be like going up like this. It can be like going down like this. It doesn't have something that is predictable. It could be moving like this, all of a sudden like this, maybe here, and so on, okay? So as you can see, if you try to fit an average over these, probably the points above and below might not be equal, right? And you need to test that. Here I have a certain average, the average drops, the average probably going up with a certain trend. So if the time series or if the variable has its mean, its variance, its covariance with its previous values, its previous lags does not stay the same, then we call it a non-stationary process or problematic process. Why is it problematic? I cannot predict it. If you ask me, if this is, let's say, the stock prices.
Can I ask a question?
Yes, sure.
Because if it's trending upward or trending downward, couldn't you predict that it would also be trending in that same direction?
You can predict probably the sign, right? But you cannot predict its value because it might also be like dropping like that. I'm just like, probably it might be going up again. It's non-predictable usually. So as I said, I have many different types of stationarity and non-stationarity. I might have a variable that is non-stationary in its variance, but it's stationary in its mean. Do you get what I mean? So it's probably like based on your question, if I have a variable like this, right? Probably like this. And if I take an average, I would say I can predict its mean. Okay, why? Because on average it's going upward. It's like the trend is going up, it's positive, it's going to increase over time. This is predictable based on the history of the variable. But can you predict the variation of the points up and below? No, I cannot predict it because at certain time periods they are tightly squeezed around the trend. Sometimes they are too far from the trend, sometimes they are way down, and so on. So a stationary process or a strongly stationary process is a process that has the same image above and below the line, and on average they are squeezed around a constant mean. A non-stationary process, I can have non-stationary in its mean, variance, and covariance. I can have non-stationary only in its variance, non-stationary it's only covariance, but stationary in the mean, and so on. So it has like different types, but I'm just going to, I'm not going to kind of dig on like the most different types of it, but I'm just going to give you like the overall picture. So let me give you some statistical ideas about the two types, okay? So let me just have it like here. So if this is a stationary series, and this is a non-stationary series, and let me give you like a nice picture. So here, for example, kind of like a very classic stationary series. Suppose that this is my 0 here, okay? And I have a certain series that is going up, down, right? And so on. And this is t, time, and this is y, t. And I do have another variable, I'm sorry, it could be like the same variable, but just a non-stationary case, yt, okay, again, over time. And I'm going to give you an image of like this, going down, like this, going way up, like this. So it's kind of unpredictable, okay? And, or actually, suppose that this is the 0 again, or actually you think of it as a variable that is going down, right? Going way from its 0, okay? So these are two different graphs, right? And let me just write it in terms of notation. So this one would be like this. Yt doesn't have an intercept, but it's a function. I'm gonna write rho instead of beta, okay? Rho is a very kind of common notation or common parameter name in time series. So rho y t minus 1, which is the first lag or the first previous value of yt, could be previous day, right? Yesterday, could be last year, whatever, depending on the frequency of the data set, plus an error term, let me call it epsilon t, okay? And we have the t, the time goes from the first year all the way to capital T, which is the last year. The absolute value of this row is always less than 1, okay? So even if the time series goes up, it will definitely go down because the parameter is less than, it's a fraction, right? It's less than 1. So epsilon, we can think of this error term has IID, okay? And it's identically independently distributed. It has a 0 mean and a variance sigma square, okay? So if this rho hat, I want you to think about it this way. If this coefficient rho hat increases, the series becomes like bigger in movements, right? But still goes back to the 0 because this coefficient is less than 1. So even if this rho hat increases, it's still less than 1. And if it is, let's say, 0.9, then it's today's value is 90% of yesterday's value. After tomorrow's value is 90% of tomorrow's value, and so on. So the most important thing is, even if this rho hat increases, it means basically that the series, right, becomes bigger in movements. That's it. And the most important thing is, whatever it's bigger in movement or not, there is a return to 0, right? So that's the definition of stationary. You go above the line, but you're gonna go back. So it's kind of a fraction, and this fraction is always less than 1. So return to 0, okay? And I should say it's a fraction in absolute terms, okay? Because it could be negative 0.9, so negative 0.9. Tomorrow's value is 90% less than today's value. That's just an example, okay? So anytime I have this row is less than 1 in absolute terms, so you have, if this series is above 0, you have downward pressure to go back to the 0, right? So you have downward pressure. And the opposite is true. If this above 0, above 1, then, right, then you have upward pressure, okay? So, or let me make it, because I want to keep the above 1 on the other side for the non-stationary. So if this is less than 1, anytime I have the series above 0, then I have a downward pressure. And also, and this completes the definition of being less than 1, anytime the series is below 0, then you also have a pressure to go back to the 0. So you would have upward pressure, okay? So that's what makes it stationary. Anytime you're here, you go down. Anytime you're here, you go up, and so on. So that would guarantee that you will always be on the 0. You will always be on the long-term average. For the other one, which is a non-stationary process, in the non-stationary process, you have something like yt is 100% depends on yt minus 1 plus the error term, okay? So in this situation, the row here, as you can see, there is no row, actually. There is no partial slope, okay? So in that case, you have actually no pressure to go back or to return to the mean or to the 0 mean that we have. So anytime I'm above, I will keep going up. Anytime I'm below, I will keep going far away from the 0. So this is a series that is a non-stationary because it would not go back to its mean. So in this situation, the movements are away from the 0, return to the 0 sometimes, could return to the 0 sometimes in the future, but there is no guarantee that it would return back. So movements are usually away from the 0, okay? So in this case, I have, it could be, let me write it here. So the row here is any number, right? That is greater or actually equal to 1, so it's not there. So in this situation, you have, you can just go far away from the 1. So what we're gonna do is we're going to talk about what's the problem of having a non-stationary process. So if I have a non-stationary process, what if I have so consequences of non-stationarity. Non-stationarity. So if I have a variable that is non-stationary, so it's a GDP, and alpha naught plus alpha 1 inflation, And suppose this is estimated, right? So it depends on inflation over time and so on. This is T. And suppose that this one is a non-stationary and this one is a non-stationary, okay? If I have two variables that are non-stationary, and so far, how can I test it? Just graph it for now, okay? But we're going to perform specific tests. So if I have two variables that are non-stationary and I do regress GDP on inflation and both are non-stationary, I will get misleading results. Why? Because this one is non-stationary, it depends on time. This one is the same, depends on time. So this one depends on time, this one depends on time. Then the impact that I'm estimating here is absorbing the effect of time. So I have to filter the effect of time out of my analysis in order to be able to get accurate estimation coefficients. So if anytime I'm regressing two variables that are, and this is very important, anytime I'm regressing two variables that are non-stationary, we will get false results, right? And you will often get very high R square. So the R square that you will get is really high and it's meaningless, okay? It's very high. It's actually a sign that you might have some kind of a problem, and this problem is called spurious regression, okay? It's a fake regression. It's a false regression, a regression of two variables that are actually linked by a third variable that is not included. And as you might expect, now time is called an omitted variable because time is affecting inflation, time is affecting GDP. It's omitted from this regression. However, it's absorbed in the coefficients that are alpha 1 and probably also alpha naught, okay? So this problem, like it's going to be really problematic the more that these two variables are connected with time, okay? If they have weak correlation with time, then probably the spurious regression is not going to be very strong. But the more these two variables are correlated with time, strongly correlated with time, I would have a more serious spurious regression, okay? So this high R square is actually due to the presence of time trend. And this is very important. So I have time trend that is affecting both variables. And I am saying both variables because the spurious regression is talking about both variables are related to time. So this is due to the presence of the time trend and not to a true econometric relationship, okay, between, here I have GDP and inflation, okay? So this non-stationarity in GDP, non-stationarity in inflation is creating a very important econometric problem called spurious regression, okay? And this is we added to the other problems that we already know, which is heteroscedasticity, multicollinearity, misspecification errors, different types, and so on. So here we have introduced a new problem. So now we come to the important point. How can I check it? So before I start estimating any time series model, I have to check my data in order to make sure that I don't have any non-stationarity issues. And if I do have any non-stationarity issues, I have to learn how to correct it before I start estimating it. So we have different ways to, so how to check non-stationarity. How to check it. So we have different ways, okay? It's all about, remember, it's all about you want to check whether the variable is correlated or significantly correlated with its previous values. Because if the variable is highly correlated with its previous values, then whatever happens in the past would affect the future. And if the coefficient is bigger than 1 or equal to 1, then I have a non-stationary process. If it is less than 1, yes, it's correlated, but it's less than 1, then we would say, okay, it's non-stationary, non-problematic process. So we have different ways of checking that. The first one is the autocorrelation function, and it's abbreviated as AC function. What is the autocorrelation function? So it's actually, it's like as the name suggests, it's the correlation. You know already what is a correlation. You know how to compute a correlation. When I say autocorrelation, it's related to the variable, how it's correlated with its own lags. So it has this notation, rho hat J. Suppose that the lags that I'm looking to test for autocorrelation are T and T minus J. So it's equal to the covariance between Y today and Y today minus J, could be J equal to 1, so T minus 1. J could be J could be equal to 2, so it's 2 periods ago, and so on, over the variance of YT. So, and you close the bracket, okay? So the autocorrelation function is the covariance between today's value of YT and a past value over the variance of today's value, okay? So it has also, I'm going to show you how it's computed in Stata. The second one is the partial autocorrelation function, and it's PAC abbreviation. This one is related to something that you know, it's partial. You know the partial slope, right? So if I'm trying to see how YT is correlated with previous lag, right? So I'm going to have it as, let's say, I'm just trying to think, let me have it as alpha, okay? So alpha YT minus 1, right? Plus a certain error term, so let's call it UT. So this one is called the partial autocorrelation 1, okay? What if I want to know the correlation between YT minus 1, YT minus 2, and an error term? So this one would be the partial autocorrelation 1, and this one would be the partial autocorrelation 2, okay? And you keep going, so I can have alpha 1, alpha 2, and alpha J, right? So you can always expand this model, and let's say we expanded and we write it as plus YT minus J. So this one would be the partial autocorrelation of today's value with the J's value or the J's year, okay? Holding constant whatever years in between. And you have to understand, remember we have still here an error term plus UT. The main difference between here and there is the partial autocorrelation holds constant other periods, right? So here, if I'm trying to find out what is the correlation between today and 2 years ago, okay, so YT and YT minus 2, then I'm not holding constant YT minus 1. Here, if I'm trying to find the correlation between YT and let's say YT minus 2, and the model stops here, then I'm holding constant YT minus 1. So I have it in my regression, okay? So the choice between 1 and 2, it all depends on what the researcher wants. To be more specific, partial autocorrelation is more accurate because it holds constant the effect of the years or the intermediate years between the period of, or the current period and the period that you want to analyze. All right. If you compute that in Stata, okay, or let me, before I show you in Stata, or I talk about it in Stata, let me talk about the third way you can test whether you have autocorrelation or significant autocorrelation or not. Is called the Box-Pierce test, and it's famous for the Q test, okay? So the Q BP, because we have another Q test. So to be more specific, this is called the Q Box-Pierce test, is actually about the accumulation, okay? So it's not testing a specific correlation between today and a certain year in the past, but it's accumulating all these values together in order to see if there is any statistical significant joint, okay, correlation between a group of periods. So it's like this. It has a certain formula, N, which is the number of observations, or let me actually write it as T, okay? So capital T, which is the total number of time series I have. Now, let me just make it, I'm sorry. Let me just make it small t because, okay, so it's a small t where T is 1 all the way to capital T. I'm not writing capital T because this would mean the very last one. Okay, so T is actually the total number of observations, and then sum from K, whatever the K is, the correlation that we're talking about. Let's say K equals 1 to H. H could be, let's say, if I want to check the correlation between 1 up to 9, okay? So H is gonna start, K is gonna be equal to 1, H is gonna be the last one, okay? So, and then you have this autocorrelation function, squared, and K. And this specific row is computed the same way that you see it here, but it's a cumulative, right? So you're going to be repeating this formula for all the years that you want to analyze, okay? Suppose that this is the first year and this is 20, okay? And I only want to check from 1 to 9, so it's a kind of a subset from my original data set. So 1 to 9, so K is 1, I'm gonna start from 1, H is gonna be 9, and T is going to be 20, okay? Suppose I want to compute the Box-Pierce test for all the periods I have, then in this situation, the K still is equal to 1, H is gonna be all the time periods I have, and T is also gonna be all the time periods I have. So the H here would stand for what is the number of time periods that you want to analyze. It's the cumulative autocorrelation of them. Okay, so when you, we have actually another test, but let me just show you in Stata. So I'm going to show you in the command in Stata. So in order to, let's say, find out, okay, the 3 tests, we have just one command. It's called CO, which is the correlogram, COGAGRAM. And suppose that I want to do that on GDP. Okay, so this is the name of the variable. And suppose I want to do that for lags, any period you want. Suppose I want to do it on 9 lags. Suppose that I have here 20. I know I have my data set is 20, but I actually want to analyze only 9. And this is just an example. You don't have to analyze always 9. Just I'm giving you an example that you can just perform it on the 9 lags. I really don't care about the last 20 years, but I really care about, is there any strong autocorrelation with the last 9 years? We can do it last 10 years and so on. So in Stata, you have to write this command. You have to tell Stata what is the name of the variable that you want to analyze, its autocorrelation, and you want to tell Stata how many lags do you want. If you don't write this part, then Stata would take the 20 time periods you have, okay? If you want to be more specific about your analysis, then you just need to tell Stata, okay, I want to do it only for the 9 lags. The output that you will get would look like this. So you will get a table that
Question, Professor?
Yes, sure.
So that won't work for panel data, right? It only works for time series.
Mm-hmm.
Thank you.
This is only a command for time series data. So you will get an output like this. The first would be lag. Second, results for autocorrelation. Third, results for the partial autocorrelation. Fourth, the Q test, which is the Pierce box test. The probability of the Q test, okay? And then you have here, it's optional here, you have here a graphical representation of the autocorrelation and a graphical representation of the partial autocorrelation. And you can write this as a graph and this is a graph, right? So these are the just 2 graphs, which are graphical representation of this and this. So what you see here, since I have, for example, in my command, I asked Stata to compute 9 lags. So this is yesterday, this is 2 days ago, or 2 years ago, 2 quarters ago, whatever your frequency, okay? And then 3 all the way to 9. And here you will get certain autocorrelation. Let's say it's gonna be like 0.96, 0.87, and any number, 0.321, for example. And the partial autocorrelation would be any number. Just notice that these 2 are gonna be the same for if I'm only having just 1 lag. So if I just have 1 lag, the autocorrelation, the partial autocorrelation are actually the same. Okay, whether I just look at this number, these 2 numbers would be exactly the same because I don't have anything to hold constant if I'm just analyzing YT and YT minus 1. So the both are going to be the same for the first lag. Suppose that this one is just any number, okay? So negative 0.61, for example, and this one is 0.07. Suppose that this is a cumulative, so the number that you get is just big, okay? And suppose that this is like this, okay? And then I'm just making up some numbers, but you can always, you will see it in Friday's recitation. This is a probability, right? Suppose that it's like this. So what, and then in terms of the graphs, it's just gonna be like something like this, okay? Showing us how the correlation looks like over time. It's probably like this. Probably 1 year is big, like that, okay? And the same for this one. It might be positive, it might be negative. So it's going to be like a graph. It's not like a graph, but it's just like an interval and showing us how the years correlate. So how can we read these numbers? So let's see if I'm trying to read this number. So this one would show that the correlation between the current value, so remember you're talking about the current value of GDP and its value 2 quarters ago or 2 years ago is 0.87. That's it. So it's the correlation between today's value and the value of GDP 2 quarters ago. I'm not holding constant the first lag. Okay, if I want to hold constant the intermediate points, okay, so let's say if I'm looking at the partial autocorrelation, I'm just choosing this one. So the partial autocorrelation would show us the correlation between, again, the current period. Every time I'm talking about the current period of GDP or the variable that you're testing and its value 2 quarters ago or 2 years ago, 2 years ago or 2 quarters ago or whatever your frequency. And this autocorrelation is 0.61. Okay, and I'm holding constant the effect of the intermediate point, which is last period. Okay, so remember that the main difference between this one and this one is I'm filtering out the effect of period 1. Or if I'm analyzing this one, then this number is telling me that the autocorrelation between today's value and 9 quarters ago or 9 years ago is equal to about 7%, holding constant all the periods from period 1 to 8. This one is telling me the autocorrelation between today's value and 9 quarters ago is equal to about 32.1%, and that's it. I'm not saying holding constant anything, and this value might be picking up the effect of previous years. Okay, so that's basically it. When you look at the Q test, the Q test is the Box-Pierce test statistic, and the null hypothesis. We have to know what is the null hypothesis of this test. So the null hypothesis, okay, is actually saying that I told you this many times. It's usually the good news, right? When I trying to test, try to come up with what is the null. So this one is telling us that all auto correlations are equal to 0 up to J lag. Okay, so let's see here. And the alternative is they are not equal to 0. I have some autocorrelation. So if I'm testing at lag 2, my null would be there is a 0 autocorrelation up to lag 2, and the alternative would be there is a non-zero autocorrelation up to lag 2. Of course, I can compare this statistic with the chi-square table. It's all made of squares. I should have written this here. Where is it? Okay, it's just, maybe it's all the way up. Okay, I should have written this here. It's a chi-square. It's made of squares, you can see. It has a chi-square distribution of certain number of restrictions. How many restrictions? How many lags I'm testing? I'm testing H, right? H could be equal to T if they are H could be equal to T if I'm testing all the lags. So here the number of restrictions I have are the number of lags I'm testing. So when I want to compare this value with the critical value, if I want to find the critical value, I just need to go to the chi-square distribution, and for this one I have to check for 9 restrictions. For the previous one, 8 restrictions or 8 degrees of freedom. For the 399, I have 2 degrees of freedom, 1 degree of freedom, and so on. It's always much easier to look at their p-value. So when I analyze this one, there is a 0 probability that the null is true. So again, what is your null? the null is saying that I have a 0 correlation up to year 1. There is also a 0 probability that the null is true, that there is a correlation up to lag 2. There is a 0 probability that the null is true, that there is autocorrelation up to lag j. In other words, all these confirming, if all of these are zeros, okay, then this is just a confirmation that I have a non-zero autocorrelation. So there is a statistical significant autocorrelation between today's value of GDP and 9 years ago, and this is an accumulative test. Okay, it's not like whatever you get here might not be the same here, because this is a cumulative test. This is a non-cumulative test, right? Again, whatever you get here might not be the same here, because this one, autocorrelation, is just picking up the effect of intermediate points. This one is not. This one is holding the effect of, is holding constant the effect of intermediate points, and it's kind of more specific test, more like filtering out the effect of the impact of intermediate points on the effect of whatever lag I'm testing. All right, so when you see the materials of the recitation on Friday, you will be performing this test and you will get all these results, okay? And it's easy to analyze. The first one, which is the AC, is like any autocorrelation, you know, you don't have any critical value to compare with. It's not a formal test. It's just a number, and it's a correlation. And this number could be any number between 1 and -1, okay? And you understand how to analyze it. For the partial, again, you know it. It's like a regression, and holding constant the effect of intermediate points. Q, it's the cumulative impact. All right. Now, there is a formal, like another formal important test. So we discussed 1 and 2 and 3 for the Q test, and number 4. Number 4 is the Dickey-Fuller test. Okay, and it's known for a unit root test. Okay, so whether the name is Dickey-Fuller test, the person who made the test, or it's a unit root test, is the same. So what is, and this is like a very important test on stationarity. So most of the research papers that you will read, you will find that the DF test is performed in order to check whether my series is stationary or non-stationary. So what is a unit root? So let's assume we have a model that looks like this. Suppose I have YT is equal to YT minus 1 plus UT, and assume that I have here a coefficient, let's say rho is equal to 1, so that's why I don't see it. Okay, so suppose that this coefficient of YT minus 1 is just equal to 1, and this means that I have high autocorrelation, right, between YT and YT minus 1. If this is the case, we call it unit root. Okay, so if I have a model that takes this form and the coefficient is equal to 1 by definition, we call it a unit root process. Okay, and under certain assumptions, which are as follows. If I have UT has the following characteristics. Number 1, it has a 0 mean. So I go up, I go down. On average, I'm on the 0 mean. Number 2, you have a constant variance. Number 3, your error term is non-autocorrelated. Okay, so if my error term has those 3 characteristics, we call it in time series UT is white noise. White noise is just a name that is very famous in time series. You can think of it an unproblematic error term. An error term that is easy to predict. It has a zero mean, like it goes up and down, it goes up and down, it goes up and down, but on average, it goes around the zero, okay? So this is the zero, okay? It has a constant variance, as you can see, like I'm trying my best to draw it, but the variation of points above and below the line, the variation is constant, okay? And it's non-correlated. So if I have all of these assumptions satisfied, we call it a white noise. And of course it has a test, but just assume that we have these assumptions satisfied. A model that looks like this, it has a coefficient of equal to 1 and its error term is white noise, then we actually call it a unit root process, okay? So now my test, or the test that I want to perform, I want to check whether this coefficient, the one that I don't see it here because it's equal to 1, it's actually equal to 1, or do I actually have a unit root process? Because if I tested and it's equal to 1, statistically significantly equal to 1, then I actually have a unit root process. If it is not equal to 1, if it is less than 1, then I will go back and to my early slide, and where is it? If it is less than 1, then I'm going to say it's stationary. Remember we said that if the model has a row that is less than 1, then I'm going to say the model is non-problematic, the model is stationary, the model is not unit root. So I want you to link non-stationarity to, let me write it here. I want you to link non-stationarity to unit roots. So a unit root process is a non-stationary process, okay? So that's why you need to check whether you have a non-stationary process. And I want you to think of unit root as being a special case of non-stationarity. Why is it a special case? Because I need to have certain assumptions satisfied. I need to have this coefficient equal to 1. Okay, it's not bigger than 1, because if it is bigger than 1, it's explosive process. A unit root is a coefficient of 1. Okay? So I want to check whether I do have a unit root, a non-stationary process, or not. So the test of Dickey-Fuller test is about the unit root test. So let me call this model as star. Okay, so I want you to think that you're testing the star model, or YT being equal to rho YT minus 1 plus UT, okay? And I call this, I'm just repeating it again. So this is the star model. And this star model, in order to check whether you have a unit root, you're actually testing this null hypothesis. You're testing whether the expectation of rho hat is equal to 1, or the alternative is the expectation of this rho hat is not equal to 1. So this one is telling me that I have unit root, okay? Or let me be more specific for the alternative. You want to know whether it's stationary. So this one is stationary. This one is a special case of non-stationary. Okay, so the test is all about this row. There is an alternative way of writing this test. So you can write the star by an alternative way. The alternative way would be like subtracting YT minus 1 from both sides. So it's going to be like YT minus 1 is equal to, I have rho YT minus 1 minus YT minus 1 plus UT. right? So what you're trying to do here is you're just rewriting star into a different version of it. It's exactly the same, just subtracting yt minus 1 from both sides. So that means this variable is the change of yt between today and its previous value in t minus 1. And I can write it this way. It's the change in yt. How about this one? I can take a common factor, yt minus 1 plus ut. So you just rewrote your model. You can just rename the coefficient. This one, you can just rename it. So you can write this yt minus 1. You can call this one whatever, any function delta, for example, any coefficient delta, for example, yt minus 1 plus ut. Okay, where this delta is simply the rho minus 1. Now, the alternative model, so I said this is an alternative model, right? So this is, I'm gonna call it double star. So double star is my alternative model, and the DF test is actually performed on this alternative model. The DF test is testing delta, okay? So your null hypothesis is about whether this delta hat is equal to 0. You know, always our default is 0 and not equal to 0. And I mean, like for the null hypothesis, our default is usually like whether this is equal to 0, okay? And the alternative is whether the expectation, I want to make it non-stationary, okay? One is non-stationary and this one is stationary, so it has to be less than 0. I want you to think about this one is the same, right, as star, because this one means if delta is equal to 0, so this is like delta is equal to 0. In other words, rho minus 1 is equal to 0. In other words, I'm just going back to the same null, which is rho is equal to 1. The same here, right? This is just an alternative way of writing it. So whether this delta is less than 0 implies that rho minus 1 is less than 0, implies that rho is less than 1. So I'm going back to the same null alternative hypothesis. So it's just an alternative way of writing it, just making your null hypothesis in terms of the 0 as we always do. So as you can notice, this is a one-sided test, whether this one or this one, they are one-sided test. They do have a critical values called the Df Dickey-Fuller table critical values. And before I talk about the critical values, I just want to make it clear again that this is a unit root, this is a non-stationary, this is the stationary. Again, here, this is the unit root, this is the non-stationary, and this one is the stationary process. So again, if I get the DF test is greater than the critical value, so you would basically reject the null of non-stationarity, and you conclude that the series is stationary. So as long as you know what is your null and what is your alternative, then you just perform the test and you conclude the same way that we do with any other test. Whatever, if I'm greater than the critical value, you are in the rejection region, you reject the null of unit root, and you have good news where the series is stationary, predictable. So let me give you an example. Suppose that I have, so this is an example, simple example. Suppose that I'm using here the alternative model, which is in terms of changes. Suppose that the change in GDP is equal to 3296, which is the, suppose I have a certain intercept, it doesn't start from the 0, minus 0.0025 GDP T minus 1. Suppose I have a standard error, 2535. Okay, the t-statistic of the intercept, I really don't care about the intercept now. The t-statistic of this one is 0.39, and suppose I have an R square of 0.0 whatever, anything, okay? Now, the DF test is about this coefficient, okay? So I want to check the t-statistic of this coefficient, and when I compare it with the critical value, it's very small. I don't have, actually, I should have the table for you, but anyway, I'm going to, there is something called the DF table for critical values, and this table is actually divided into 3 parts. One for whether your series does not have an intercept, so no constant, no trend, like it does not depend on time. Another version, whether you have a constant or an intercept, and again, you don't have any time trend, and I'm going to explain that. And then you have here a constant and trend. So which one I'm going to choose? And each one has like this different significant levels, 1%, 5%, 10%, same, 1, 5, 10, 1, 5, 10. So which one I'm going to choose in order to find my critical value? In terms of the constant, yes, I have a constant here. So definitely I'm going to look for a constant, right? So it's either this one or this one, but not this one, because my model, I have chosen to estimate my model with a constant, right? Or an intercept. Next, what about the trend? If you graph your variable and you find it like going certain relation with time, and this is time and this is GDP, then you would say, okay, it seems like it depends on time. So I'm going to choose a trend, okay? However, if you graph your variable and you find it somehow like this, which is unusual, right? It's the time series, usually you have some relation with time, then you would say, okay, it seems that I better use no trend. Okay, so you have critical values that depend on how your model looks like, whether you have a constant or an intercept or not, and whether your variable, if you graph it, looks like it depends on time or not. Anyways, this I will like give you the table next time, but this t-statistic it seems like very low. So I'm sure without looking at the table that this is insignificant. So, and I'm going to show it to you next time. So suppose that I find that, let me write it here. Okay, so based on the model I have an intercept. So I'm going to choose the table of DF table that has an intercept, and suppose GDP depends on time. So I'm going to go to this version of the table, constant and trend, okay? And in this case, I'm going to say, okay, the 0.39, which is my t-statistic, is below the critical value of the DF test for this version of the table, okay? And you're actually going to fail to reject the null. And what is the null? The null is actually, when you go back, what is the null hypothesis? The null hypothesis, I fail to reject the null, right? Just keep going. The null is saying that this coefficient is equal to 0. What is the meaning of delta being equal to 0? It means that rho minus 1 is equal to 0. It means that rho is equal to 1. It means that I have unit root. So I fail to reject the null of unit root. My conclusion is the series is non-stationary. So you would write that here. Fail to reject the null, conclusion, non-stationary. Okay, so GDP is non-stationary. Okay, and this is again a critical value from the DF test, from the DF table. Okay, now One thing before I leave the DF table, like talking about it, I want you to note the following. They call the constant another name, or the intercept, it is called another name, okay? It's called drift. So drift is another name of an intercept in time series, okay? So this is called drift. So the critical value I'm using is a model that has a drift, right? And time trend. So this is the model that you're using for this specific model, assuming that I have graphed the model and I find there is some tendency to move with time. So that's why I decided to choose this shape. Okay. Any question? Any question? All right. So what else? An important thing to note the following. The DF test has different versions. What you see here is a very, very simple version in which I'm testing GDP depends on one lag. However, it might be the case that I'm actually analyzing more than one lag. So I'm not going to show you the derivation of the more than one lag, but I'm going to show you the final outcome. So the final outcome of a model that, or an expanded version of the DF test, okay, or it is called the, I'm just gonna write in white. It is called the Augmented Dickey-Fuller Test, and it's abbreviated as ADF test. Looks like this. The change in YT, there is a certain intercept, right? This is the coefficient that we're testing, YT minus 1 plus beta 1, the change of YT minus 1 plus beta P. Let's say this is our last year, change of YT minus P plus UT, okay? So this is an expanded version, or we call it Augmented DF test. And this Augmented DF test, we have the same null hypothesis, and the null hypothesis is performed again on this one, okay? So again, we have the same null. So whether this one, this delta is equal to 0, and the alternative is whether it's less than 0. And again, this is the unit root, and this is saying stationary. So if you're testing more than 1 year, you still have the same null hypothesis to be tested. Also, one last version of the test is, what if I want to include time trend, okay? So I have the Augmented Dickey-Fuller Test with time trend. Time trend, just like you're adding time trend. So YT has a certain intercept, but it also depends on time. So alpha here is a measure of the connection between GDP, let's say, and time, okay? Where time is, let's say, if I have from 1 to 20 years, then T is gonna be 1, 2, 3, 4, 5, all the way up to 20. Plus delta YT minus 1 plus, and I'm going to continue this part, just copy paste. So plus beta 1 change of YT minus 1 plus keep going plus beta P YT minus P, and there is a change here, delta here, plus UT. And again, your test is the same null. Okay, so again, you're just testing, but here you accounted for the time trend. So just to complete the picture, so this one is the ADF with time trend, so you're accounting for time. This one, the drift, and this is again the drift. So this one would be a model that is, or ADF test with a drift, no time trend, ADF test with a drift and time trend. And just some people, they want to be on the safe side, they would always use this general version where I have the time trend. It might turn out to be insignificant, but you have it just to test it first. Some people, they would just look at the graph. If they find it starts from 0 and it moves like this, then there is no constant, there is no drift, right? But there is a trend. If you find it like this, right? And this is, let's say, any number, say 5. So I have an intercept of 5. Then here I have a drift, no trend, and so on. So you have like different formats of the model, and you choose the one. You can depend on the graph and to decide, or as I said, some people, they would go with the general version, and it might turn out to be the case that alpha is insignificant, so you don't need the time. And if this is the case, you go back to this model. All right. I'm going to stop here, and we will continue on Thursday. Any question? All right. Okay, so I'll talk to you on Thursday, and enjoy the rest of your day. Thank you.